was not doing that. But let me just say from the very beginning that an Atwood machine problem as a physics example is supposed to be a way of exaggerating the relationship between applied force and inertia. That's what the problems are really about, giving you a clear connection between the applied force and inertia. They all use gravity, and they use gravity in a way to demonstrate an unbalanced force, and then they use the mass of all the things that are moving as things that contribute to the inertia. We are going to break these up into small pieces and do them a little bit at a time, starting with systems in which our pulleys have a mass of 0 and are not contributing any inertia to the system. Second semester, that's gone. We'll deal with rotational inertia, and we'll have to deal with the fact that our pulleys, as they spin, require unbalanced forces to get them to move. Massless pulleys have a specific contribution to these problems. They make the tension anywhere in the cable the same value. Something we've kind of talked a little bit about already, but once the pulleys have mass, that won't be true. The pulley itself is going to require an unbalanced force to spin, in which case that's going to basically take some of the tension away from one side in order to allow for an unbalanced force to turn the pulley. But for the time being, we're going to focus on problems in which the pulleys are massless. So I'm going to take and look at the modified Atwood machine first. They're a little bit simpler. And for this particular example, we're going to start with a situation in which the surface is frictionless. Let's go ahead and label this M1, this M2. And again, we're going to say that our pulleys are massless. Now, the pulley is experiencing forces. I've left this out of all the other classes, but since there's so few of you, you'll get the secret knowledge. You can look at net force acting on the pulley. If it's massless, there are 3 forces that act on the pulley. There's 2 tensions, one to the left and one downwards. And then there's the mount that mounts it to the table. It's applying a force, like a normal force, to hold the pulley in place. So there's no reason we couldn't at any moment kind of identify what's happening to a pulley in one of these problems. Second semester, we will a little bit more. First semester, we're going to kind of leave the pulleys out and just kind of focus on them being nothing more than a way of redistributing the force, basically taking a tension and turning it into another direction. These problems are not hard, but having never done them before, a lot of students kind of balk at what they have to do. But you've already done the work for these kinds of problems, meaning you could begin the problem understanding that there is a downward force here and an upward force. That's it. We've kind of done that. Here's where I'm going to expect a little bit more from you. When I look at what's happening to M1, the sideways tension on M1, this arrow should be the same size as this arrow. They represent the Newton's third law pair, so they should be equal sized forces and generally in opposite directions. The pulley's getting away of that, but they represent a Newton's third law force and are therefore equal and opposite. Now, of course, we're still going to have weight and normal, but those don't really contribute very much to this problem as there is no friction, nor is our surface at an angle. Now, here's where we probably need to add something. At this point, everything we've done here has been stuff we've done before, with the only exception being we had to recognize our Newton's third law pair. But there is something else we need to do, and that is a recognition that the box on the table cannot move without the box that's being hung also moving. Can we all agree with that statement? And does it make also perfect sense that the amount that each box moves has to be the same? Now, that doesn't have to be true. There are plenty of pulley arrangements where one object can move more or less than the other. But for this one, we're just redirecting the force. So the acceleration of one box has to be the same magnitude as the acceleration of the other box. Does that seem fair enough? Like if one box moves a meter, the other one moves a meter. What I would encourage you to do is to unify the direction of motion for your problem. Now, the way I teach this is different than the way the book teaches this. The book has a different method. And I don't like the book's method. I think it's harder. But if you don't like what I'm showing you, then definitely look at the way the book does it, because it is distinctly different. I identify what I think is the likely direction of motion, and I call that positive for everything in the problem. I've been talking about this all year, and I've been trying to be consistent, but I identify what the direction I believe the system is going to move. This is a little more complicated. More than one object is moving. But I'm saying that this way is positive for the mass that's hanging, and this way is positive for the mass on the table. I don't care about other directions, so they'll work themselves out, but when it comes to the direction of the acceleration, I'm identifying it to be consistent across the board. Now, your book does it different. Your book would have you draw a coordinate system the same way for every object, with positive and positive, negative and negative, but then you have to go object by object and identify direction for acceleration as well as force. I think that's harder, so instead, I just have us choose this direction from the beginning of the problem and make everything conform to that. So if you don't like my version, check out the book's version. It's different. It's probably more accurate. Actually, it's not any more accurate. It's just different. So there's not a whole lot here. Can you write a set of force equations that kind of set up this problem? I think you guys know Newton's second law, so take a second. It's better if you do it first than I do it. And that should be enough time. The box on the table, T equals M1A, right? There's a single unbalanced force acting to the right, and therefore it's going to accelerate, and the amount of the acceleration is based on the mass times A. That good? M2G minus tension equals M2A. That seem appropriate? No troubles here? All right, that is Newton's laws. You have applied all of the rules. This is it. Now, granted, there's two objects, and there's probably more to do, but this is what you get if you just follow the rules that we've had so far this year. It will generate a relationship. The difference is this relationship has two variables in common. We've already agreed that T has to be the same due to Newton's third law. A has to be the same because the things are connected together. So generally, from this point, it's either finding the size of an individual force or finding the size of the acceleration of the system. I would encourage us to do the acceleration first. It's almost always easier. And that's just simple substitution. Now, I'm not going to do simple substitution. I want you to see something here, that just like with the train problems, we can, if we've chosen our direction consistent for all the objects in our problem, we should be able to stack them and just add them together. Internal forces should cancel out, and all that will be left will be the external force and the inertia of our system. So it should be just like what we did with the train problems. You'll notice the two tensions do cancel out when I add these down, and I'm left with M2G, M2G equals M1 plus M2 times A. This is the inertia of the system. If you've done these problems right, you should always have an equation at the very end like this, where you see the sum of all of the inertias of the system. That's how you know you've done this right. This is no different. And when we start adding in the pulley, there'll be another thing there for the mass of the pulley. Every time we do one of these problems, we should see the sum of all the masses end up somewhere. More importantly, when we solve this for the acceleration is net force divided by inertia. You will always see the sum of masses in the denominator of these fractions. It's an easy way to go through multiple choice questions and identify the answers that are unlikely to be true. If they don't add together all the masses and have it in the denominator, then that's not likely going to be the acceleration. Questions to this point? Is this not so bad? They get more complicated. This is as easy as they can be. If you want the tension, you just substitute back in. There's not a whole lot there, but this would have to be the tension. Just take this and plug it in over here. And that gives you the tension. I'm going a little fast because things are going to happen fast here, but any trouble with any of that so far? Really? Well, let me see if I can catch you, all right? I want to point out these are supposed to be exercises in inertia, but students are sometimes easy to trick. So let's see if I can catch you or trick you. It sounds as though something is happening. I don't know, do you hear something? I find it funny. We try to try to keep going, try to do, school stuff as if it's, there's nothing else going on, but let's face it. Sometimes that's just hard. It'll be Mr. Bear who will do all the announcing. Nobody likes being on that mic more than Mr. Bear. He's a bit of a glory hound. So I like Mr. Bear. You guys know Mr. Bear? Yeah, good guy. So. So it took a little time for me to draw this out, but I wanted to compare these two systems, okay? 5 kilogram box has a weight of 50 newtons, right? 5 kilograms would be 5 times G or 5 times 10, that's 50 newtons. So the external force on both of these systems is 50 newtons. Which one accelerates faster? The one on the right or the one on the left? Or are they the same because they have the same external force? Now, I'm asking this because you should be able to figure out why this is a question. I'm clearly trying to lead you someplace here. I should also ask you, in which case is the tension greater? Does the one on the right have greater tension in the cable, the one on the left, or are they the same? Now, I'll remind you that an Atwood machine question is supposed to be an exaggeration of inertia. And to answer these questions, I want you to think about a few things real quick. First, in one of these instances, something external is applying a force to our system. In one of these, something that is part of the system is applying a force to our system. So, in which case is more mass moving? The one on the right, the one on the left? Do you know the answer to that? Because that's the answer to the question. 15 kilograms of mass is being moved on the left, while 10 kilograms of mass is being moved on the right. The system on the right has less inertia, therefore will accelerate faster. The system on the left has more inertia and will therefore accelerate slower. If we think of it from this standpoint, net force equals MA, It's 50 newtons is the unbalanced force for both of them. So the acceleration here has to be 5 meters per second squared. I have an unbalanced force of 50 newtons acting on a 10 kilogram mass. But the acceleration here, 3.3 meters per second squared. A 50 Newton force acting on 15 kilograms of mass. Tension in the cable, it's 50 newtons on the right. Has to be. But on the left, not so much. There must be less tension upwards than the weight downwards in order for that block to accelerate. So the tension has to be less. This kind of question is not hard when you think about it from the right vantage point, the standpoint of inertia. But if you try to employ the idea, well, they're both experiencing the same force, it'll take you down a dangerous road. When you only have 1 minute and 15 seconds to make a decision, because you know that this is multiple choice, right? Do you see why it's going to be easy to trick you? Let's take a look at the next most likely. And I didn't make these problems up, folks. These have been tricking students since I was a student and I was tricked. All right, 5 kilogram box, okay? It is attached to the table, right? I have something on the table like that, that little lip on the table up there. I tie the string to it. 50 newtons of tension in the cable. That seem okay? Right, the box isn't gonna go anywhere. So if it's attached to the cable like that, would you all agree there's got to be 50 newtons of tension in the cable? You don't seem like you're convinced, but I'm not trying to make this hard. If I tie it on here, and this is 50 newtons, it would have to be 50 newtons of tension in the cable, unless the cable were to snap and the box was to slide, to fall to the floor. So the real question comes down to, what if instead I had another box. Oops, it's not another box. And another pulley. Now I'm hanging 2 boxes from the same cable. The boxes are the same weight, but I'm hanging 2 boxes from the same cable. Does this increase the tension in the cable because the cable's having to hold 2 boxes and not 1? Thoughts? None? Are you being tricked? Do you think I'm trying to trick you? I mean, I am. Are you tricked? Go ahead. Do you have an idea there, Adam? You're going to help me out anyways, Adam, okay? Sorry. Just look at one box. How much tension has to be in the cable? 50 newtons, yeah. There's nothing different here. Hanging 2 boxes tricks you into thinking that the cable somehow has to do more than it's actually doing. The difference between having the box on the side and having the table on the side, the piece of table there, the only real difference is that one of them is helping make sure there's tension in the cable enough. If I don't have this box here, and we just tie it to the table, all the table is doing is providing 50 newtons of tension to the cable by not letting the cable fall. If I move this away, something else has to provide that 50 newtons of tension to keep the box from falling. So anything can be used for that can provide 50 newtons of tension. A 50 Newton box will do that. But we tend to think that there's something different about the cable here, but there isn't. The cable itself still has 50 newtons of tension in it. Again, these kinds of problems are problems that are designed to interfere with your conception of what's happening. And you'll let them if you're not careful. So if you want to be able to analyze any of these when it comes to force, stop thinking about all the elements and look at one element at a time. A single element can tell you what's happening in the system. Let's go back. Actually, we can just use this picture. I want to make sure we understand, too, that it really doesn't matter whether we deal with a system that has no friction or a system that has friction. Arguably, the work ends up being the same. Let's not have numbers. Let's just deal with this from a standpoint of M2, M1, and now let's have a coefficient of kinetic friction here. So similar question, but I'm just going to give the box a tap to break static friction, and the box is going to accelerate. Take a minute and free body diagram. Work out your force equations. Think about 1 minute should be enough. Maybe 2. I'll give you 2. 120 seconds. It's just things we talked about. Did you pick a direction you're going to call positive for all the objects in your system? Start there. Did you draw a free body diagram that identifies the forces acting on each object? Were you careful to identify any force that might be shared between two objects and make an attempt to make those forces look the same? At the same time, did you recognize that for the box on the table to accelerate to the right, the friction would have to be less than the tension? And did you now recognize that you are going to need to identify and deal with the normal force since you have a frictional coefficient? It's a lot. Staying in that vein, normal is equal to M1G. Friction equal to mu times normal force. Tension minus friction equals M1G. You combine all of it together. Tension minus mu M1G equals M1A. I'm sorry, that should be M1A right there. Thank you for not calling me out on it. Net force equals MA, sorry. Maybe I've done this more than one time today. I'm just getting done with it. That's just applying the rules to the left box. The right box is even easier because nothing has changed about the right box. M2G minus tension equals M2A. We're done. Got a couple of relationships that have some shared variables in them. I'm looking for, expressions for acceleration and tension. Now, I'm mostly interested in looking at the acceleration right now, so.
Pardon the interruption. At this time, please send down only the following groups of students.
Okay.
Golf, volleyball.
So, I kind of want to cut through this real fast. Have you guys realized we're just going to combine these together the same way? T's are going to cancel out. Be left with M2G minus mu M1G on the left side. That's adding this and this together. T's cancel. The right side, M1 plus M2 all times A. Now, I like this. And you know, I'm going to say some stuff here about this. You know, I do my M2G minus mu M1G all over M1 plus M2. I have my sum of masses, so the inertia is here. I have my two external forces. One that is trying to cause the system to accelerate, the other one trying to stop the system from accelerating. Minus sign, right there, seems pretty important to me. Anytime there's a minus sign, I like to stop and take pause. It means that this system could accelerate to the right, could accelerate to the left, or it could not accelerate at all, right? This could be positive, that means accelerate to the right. This could be negative, which means accelerate to the left, slowing down. Or it could be zero, which means it moves at constant velocity. There are three possibilities there. Now, I am not going to do this next part because this is mechanics, and I expect you guys to have a little bit more flesh in the game, so to speak. You should solve for tension and come up with an expression for tension. It's not obvious what the answer should be because the tension is either going to be less than the weight that is hung, the same as the weight that is hung, or greater than the weight that is hung. It won't be negative, but it could be any one of those three things. Because if it's accelerating downwards, then M2G is greater than tension. If it moves at constant velocity, then M2G should equal the tension. And if it's slowing down, then tension should be greater than M2G. This expression should show that. You should find that expression. You should do the substitution and work it out. All right, I know it's the end on a Friday. There's just one. Well, there's lots more. I have to put the whole thing on an incline. Put the box over there. Put that like that. I could turn it into a train problem. Putting two boxes here, connected by a string between them. And then I can put, our pulley here, and another string here, and have this go to a box. Now I think we're talking about a test question now. This one looks good. Yeah, I like this one. Serve those band kids right for leaving. It looks more complicated than it is. This is just a modified Atwood machine problem. We look on this side, you can treat that like one box. That'd be fine. I treat it like one box. The only difference now is I've got other forces acting. We've dealt with an incline before. Pick a direction that you think is positive and work through it. There. That was just for fun, though. I mean, don't get me wrong, that could be on the AP exam, no worries. But let's look at the one problem that I need you to kind of pick apart before we leave. And go enjoy our homecoming pep rally after homecoming. And although a successful homecoming in that many people had fun, I would say it was also successful at spreading a wonderful cold that everybody seemed to catch at homecoming. And I've been so happy to have everybody come and cough up their mucus in my classroom the whole couple days. That's been good times. So I'm sure you've been hearing that in all of your other classes. The wonderful sound of all class period long. It's been good stuff. That's what a good homecoming will actually do. Spread an illness. All right, so a standard Atwood machine problem. Now, there's no way to know if M1 or M2 is greater. There's no way, especially not in a situation like this. So you just pick a direction and call it positive. Doesn't matter whether I pick left or right as positive, clockwise or counterclockwise. Just pick a direction and go with it. If you work it out, you'll find out that your answer will tell you whether you're going to have a positive or a negative for your acceleration. But the mistake students are going to make, one of them is just not actually doing this, but the big mistake is going to be your free body diagram. We've been talking about starting all of these problems as if the weight was the thing that would drive what you should do first. For a problem like this, you should make it the tension. Because with the pulley being massless, the tensions have to be the same on both. And this is where I'll be very critical of your drawings when it comes to the size of the arrows you draw. Regardless of what direction this accelerates, the two tensions should be the same. If I think it's going to accelerate clockwise, then I'd have to draw M2G to be larger than the tension. So it's unbalanced downwards on the right, which forces me to draw M1G shorter than the tension, so it's unbalanced upwards on the left. You have to be aware that your forces have to be in agreement and the proper balance has to be shown. Either way, it's going to be M2G minus tension equals M2A on the right, and T minus M1G is going to equal M1A on the left. Again, if you don't show consistency for the direction of motion, your signs will be wrong and you'll have trouble. But if you've been consistent, you should have one with positive tension, one with negative tension. Add them up, and you'll get M2G minus M1G, no tension. And that has to equal M1 plus M2 times A. You should get the sum of all the masses as part of what happens as the course of your problem. Now, you saw for the acceleration, that part's not hard. And I think this is kind of obvious, but maybe not. This is the net force. If M2 is bigger than M1, it accelerates in the positive direction. If M1 is bigger than M2, it accelerates in the negative direction. Duh. But the heavy one on the left, it accelerates towards the left, but the heavy one on the right, it accelerates to the right. If they're the same, they don't accelerate.
Good afternoon. So today we have two options for students. Students, you are encouraged to join us at the pep rally here shortly, but also if
you should prove this to be true. It's not easy. It's some icky math. But you should plug this back in to one of these and find that for the tension. It's icky. It's no fun at all.